Hello everyone, I'm Abhi Lad. The paper that I will be presenting today is from my bachelor's thesis under the guidance of Dr. Reema Patel. Currently, I'm a research engineer at Origin Health working in the field of medical imaging AI. So let's start with introduction. What is the task at hand? What we want to do is to reconstruct images seen by a person from fMRI. So when we look at images, neuron activations occur in our brain, which are recorded as fMRI signals. We want to reconstruct images given an unknown fMRI. So why do we want to do this? What is the motivation? So the first and foremost is to visualize dreams. This is the end game. Visualizing dreams will help neuroscience field understand the human subconscious. Another motivation is to study brain functionality of comatose patients. If we can understand what the patient is visualizing, maybe we can provide an external stimulus to treat them. Another possibility is the interaction between brain and machine. Instead of an intermediate medium, brain can directly communicate with the machine. So let's take a look at the dataset. When we see an image, the visual cortex processes this information. There are specific regions which recognize color, shape, face, and many other things. This happens by firing of neurons in response to the visual stimulus. But we cannot capture one-to-one correspondence of the neurons. Instead, what we capture is oxygenated blood flow, that is bold data. And that coarse representation of neuronal activity is what we term as the fMRI. So what are the challenging factors that makes it difficult to do this task? For one, the sample size is small. Second, the input dimensions of the fMRI are large. It may not seem like 4,500 is a large value, but considering the fMRI are subjective, this is a large value. And third, and the most crucial factor is inherently noisy data. Suppose during fMRI capture, a dog is shown to you. And if you have a pet dog, there is a possibility that your brain imagines your dog, which introduces noise to the data. So how do we do this, converting the fMRI to image? So one is end-to-end approach, where we train an image generator or a decoder to generate images directly from fMRI. However, due to limited training data, this results in poor generalization. Another approach is a decoder-based approach. Here, we can train a decoder to generate image features from fMRI instead of directly generating image. Then we can use this image features to train an image generator network. What is good about this method is that now, since the image generator network is independent of fMRI, what we can do is that we can train the image generator on external images. Basically, what we do is we extract image features from other images and train our image generator on those images. Now to the method which we propose. So it is similar to the decoder-based approach. We use fMRI to generate image feature and train the decoder using the image feature loss. But we don't stop here. What we do is we use this decoded image features to generate an image. And then we calculate the loss of this generated image with that of the original image and use it to train our decoder. The image generator is already trained on external ImageNet images, and we only train the decoder during this routine. The rationale is to make the decoder output consistent with the input distribution with which the image generator is trained. This part is what we call the purpose-based training, because the purpose of the decoded image features is to generate image. Looking at our image generator model, the input to the image generator model are the image features extracted from the last convolutional layer of VGG19. We pass it through a fully connected layer and then through an inverse convolutional equivalent of VGG19. This generates an image. Now, this whole network is trained in a GAN-based approach where we have a discriminator which identifies whether or not the generated image is realistic or not. For our decoder, we have fMRI as an input to the decoder. The decoder is a standard 2 hidden layer, 1 output layer model, neural network model, where both of the hidden layers are followed by Salo activation. This results in the decoded features which are fed to the image generator network to generate images. Now, for understanding what are the losses that goes into training the decoder. We term the image loss as L-gen and the feature loss as L-feed. Looking at the image loss, it is a weighted loss of binary cross entropy and mean absolute error. The mean absolute error is calculated with respect to the image, generated image and the actual image, whereas the binary cross entropy loss is calculated on the output of the discriminator which goes into training the image generator network. L-feed is basically weighted summation of mean square error and cosine error, both of which are with respect to the generated and the actual decoded image features. So the total decoder loss is summation of L-gen plus L-feed. A look at a qualitative results. So here we have original images followed by the results from our proposed approach. Then we have images from model which is trained only on L-feed, not on the L-gen, not on the purpose-based training, that is. Then we have results from a model where decoder is basically a ridge regression model. A ridge regression model is the de facto model used to map fMRI signals. As you can see, the image from our proposed approach are significantly better in terms of color and structural reproductions. Now, here we can see the results of our approach on the different test subjects. Models are trained and tested individually for each subject due to varying fMRI dimensions. Results are more or less consistent across the subjects. For quantitative analysis, we use two-way pixel-wise comparison. The original image is compared with the image generated from its respective fMRI and from an image which is generated from an MRI which is randomly selected from the test set. Now, it is considered a loss if the image generated from the randomly selected fMRI scores higher, and it is considered a win if the respective image generated from the MRI corresponding to the original image scores higher. We use Pearson correlation coefficient as the pixel-wise comparison function. For each image, 49 such comparisons are made, and we have 50 images in total in our test set. So that results in total of 2,450 comparisons. As it can be seen, our method where the decoder is trained on image loss as well as the feature loss with 81.3% winning scores higher than both of the other decoder approaches discussed in the literature. We have refrained from using human voting as a comparison metric due to subjective biases. To summarize, we have managed to improve the image reconstruction from unseen fMRI by training the decoder to match the input distribution of the image generator. Now, this method which we propose is not limited to the task which we discuss here, but can be extended to other tasks, albeit with proper validation. Thank you, everyone.